So hello folks, welcome to yet another session. Today we are going to talk about rate law and rate constants. In our previous topic we touched on rates of reaction, and we said that the rate of a reaction is the concentration or the change in concentration of the reactant or products over a certain period of time. Now, the rate law is an equation that expresses the rate of the reaction as a function of the concentration of the reactants, and it's given by, so the rate law is equal to K raised to power A M and B raised to power N. Now, this is what we call the rate law, whereby K is our rate constant and M and N, which are the powers, the concentration of the two reactants, what we call the reaction order. So, what you need to note is that the reaction order does not or may not reflect the stoichiometry of the reaction. So, it does not follow the stoichiometry of the reaction. So, this can be different from the stoichiometry of the chemical equation. So, the reaction order, or the order of a reaction, is the power to which the concentration of the species is raised in a rate law. Now, example here, M and N, and is determined experimentally by the formula rate is equal to the rate constant multiplied by the concentration of the reactants. M and N in our case, and they give us the reaction order. We have something we call overall reaction order. So overall reaction order is the sum of the individual orders. So in this case, the overall order will be equal to M plus N. Now that is the overall order of that reaction. Reactions called zero order reactions. So in these reactions of the zero order rate law, these are reactions in which the concentration of the reactants is independent of the reaction progress. It's a rate law in which the concentration of the reactants is independent of the rate of the reaction. Therefore, there is no significant change or no significant connection between the rate and the concentration of the products, of the reactants. So that is what we call a zero order reaction. A reaction in which the rate and the concentration of the reactants is independent of the rate. No matter if you change the concentration, the rate of the reaction still remains the same. And the negative order, the reactant is an inhibitor and slows down the rate of that chemical reaction. So what you'll notice is that the overall rate constant will be moles per second. Simply because this and this cancel out, this and this, one of them cancels out, and therefore we remain with the second. So the rate constant has the formula in moles per second. So that are the units for it. So it's given by the units of rate over the units of concentration. So the units of rate are in moles per second over the concentration, which is the moles per liter. If it is a second order reaction, raised to that power. So what you'll observe is in this, one of them cancels out. And if you forget moles, that will be the overall formula for a second order. So we're going to work on one example whereby NH4, you've been told that using the rate law, this calculate the rate for this reaction given that the concentration of ammonium ions and the nitrate ions is 0.1. So this one is direct, so the rate will be equal to 0.0, will be equal to 2.7 times 10 raised to the power negative 4 multiplied by concentration of the ammonium ions, 0.1 m, multiplied by the concentration of the nitrate ions, 0.1 m. So what do you get? So you'll get 2.7 times 10 raised to the power negative 6. What do you think would be the units? The units for rate, as we said, are given in moles per second. So that will be our rate for that chemical reaction. So next we're going to look at something we call rate law determination. For the rate law determination, this is simply I determine the rate law using various ways. We have several methods. One of them is isolation method. And the second method is what we call the initial rate method. And the third one is something we call the graphical method, or the one-off method, or the log method. So in the isolation method, we normally have two reactants, let's say A and B. Now what you normally do, you get the concentration of A, and in the other one you put B in excess. Therefore our reactant B will be in excess. Therefore, when you're determining the rate of that chemical reaction, get that the rate is equal to K A, and here we have B, B is in excess, we can approximate that the rate order with respect to A will be only due to the concentration of A. We call that the pseudo first order rate law. Therefore, here we have that the rate will be equal to K raised to power A, and that is our pseudo first order rate law, whereby we only consider A in our case over here. Then in the second step, now we repeat the experiment, and in this case now in step 2, what you'll do, you'll now do the opposite. Now our A will be in excess, and then our product B will be fixed. So when you're determining the rate of that concentration volume, the rate, it will be only due to B. So that will be the other pseudo first rate order for B. Now the rate will be K. Here we have A, and here we have B. But in this case, our A is in excess. Therefore, what happens? The rate will be due to this, which is fixed, or which is proportional. Therefore, the rate at this point will be the pseudo first order rate law for our reactant B. So after this, what you'll get after isolating both, now from this point we can determine the overall rate law. Because at this point you'll get the rate for this, and you have the concentration for this, you'll get this, and here we have the concentration of the other one. So you combine the two from the two equations, and that is how you determine the both for both the two reactants and the products. That is the isolation method. Rate method. So in the initial rate method, we measure the rate at the beginning of a reaction for several initial concentrations of the reactants. So it is used in conjunction with the isolation method. So if the reaction is zero order, it means that the change in concentration has no effect on the rate. And if it is a first order reaction, the change in concentration brings a proportional change in the rate. Doubling the concentration doubles the rate of the chemical reaction. If it is a second order, doubling the concentration increases the rate by a factor of 2. So let's say, for example, the reaction is a second order. If it's a second order reaction, if the rate, let's say, is 2, or let's say the concentration is let's say 3m. After we take, let's say, a second reaction, and we double the concentration to 6m or 6 moles, what you'll observe is that the rate or the concentration, the rate of the reaction will be raised to a power of 2 raised to power 2. 2, this is the reaction order, and it will be doubled. Therefore, it will be raised to a factor of 4. That is what you will accept, or you will see in a second order reaction. If it was a first order reaction, for a first order reaction, the rate will be doubled. Therefore, the rate will be twice the concentration. Or what you observe is that the rate of the first reaction and the rate of the second reaction, it will be doubled. So it will be 2. Now, we are going to do an example of the initial rate method. So we are going to dive into this example over here, where we have nitrogen and oxygen combining to give us nitrogen 2 oxide. So we have the experiment 1, 2, and 3, and the initial rates. I have the concentration and the initial rates of the reaction. So the question asks us to determine the reaction order over here and the rate constant K. So what we first do, we take the ratio of the two. As you can see here in the first reaction, the concentration of nitrogen is kept constant, while the concentration of oxygen is halved. And as you can see, the initial rate is changing by a factor of a half. Therefore, we can take this and say that rate 1 over rate 2 will be equal to, now for the first reaction, see that K N or 2 raised to power N. Where is our oxygen? Our oxygen O2 is 2.0 times 10 to the power negative 3 multiplied by our nitrogen here, which is 4.0 times 10 power negative 3 moles all over K multiplied by our H2 here. Oxygen is, and remember, this is raised to power N and this one is raised to power M. This one will be 1.0 times 10 raised to power negative 3 power M, now power N times our second rate for nitrogen will be 4.0 times 10 raised to power negative 3 So that is what you'll observe, and what you'll see here, so this raised to power M, the rate, we have the rate for 1 and the rate for 2, which are here, over here, so we can substitute them here. You'll get that 1007 divided by 500 will be equal to this, and this cancel out since they are the same, they are similar. We remain with the rate constant, and the rate constant cancel out because they will be similar, and therefore we remain with the 2. As you can see, when you divide this by this, you get 2, simply because this and this cancel out. 1 divided by 2 is 2 raised to power N. They are both the same, so this raised to power N will be 2 over 1, or however much you would want to do it. So 2 raised to power N. So this divided by this, what do you get? 1007 divided by 500, we get is 2.014, which is equal to 2 raised to power n. So how do you get this factor? To get the factor, you take the log for both sides, or the natural log of 2.014 is equal to n log 2. Therefore you divide by 2, and you get that n will be equal to, let's divide by log, natural log of 2 1.01006, which is approximately 1, isn't it? Moving to our second part of the question, where we had now step 2 and experiment 2 and 3. Now in the second experiment, we were told that oxygen concentration was kept constant and the concentration of nitrogen was halved again. Therefore, if you take the ratio of the two, take, let's say, the rate of 2 or rate 2 over rate 3, what we get here is the rate constant of oxygen raised to power m over of nitrogen raised to power m all over the rate constant of oxygen raised to power n and nitrogen n2 raised to power m. So these ones will be given by 500, which is the rate of 2, by rate 3, which is 125, is equal to K, the rate, the concentration of oxygen in that case is 1.0 times 10 raised to power negative 3, and the rate for nitrogen, this one is raised to power n, and this one is 4.0 times 10 raised to power negative 3n raised to power m. Now all over K 1.0 times 10 raised to power negative 3 raised to power n, and here is 2.0 times 10 power negative 3m. Now what we do, these ones cancel out because they are similar. This and this, they are equal. The K and the K, they are the same. Therefore the rate constant will be, or the rate on this side, the ratio will be 500 divided by 125 is equal to what? Is 4. Because 125 times 4, or rather 125 times 2, you get to 50 times 2 is equal to 500. Therefore 500 divided by 125 is 4. Therefore this will be equal to this over this. As you can see here, 4 and 2. So this one is simply saying 4 divided by 2 is 2. This one will be 2 raised to power m. Isn't it? Now we make the base to 2. So we say 2 raised to power 2 is equal to 2 raised to power m, that is simply indices and logarithms. Therefore, after getting this, we know that our m is equal to 2. That's right. Therefore, we've determined that the reaction order for the 2, let's say for N2, which is our nitrogen, is equal to 2, and for our oxygen is equal to 1 and is equal to 2. Therefore, using this expression, we can get the rate constant given. So we can take one example or one equation from those, and we can say that the rate constant K is given by the rate divided by the concentration of nitrogen raised to its order, which is m, and oxygen raised to each order, which is n. Now, let's say, for example, we take the first experiment where we have the rate is 1007 all over. Here we have the concentration of nitrogen as 4.0 times 10 raised to the power negative 3, and we saw that the reaction order for the nitrogen is 2. Then here we have the reaction concentration of oxygen as 2.0 times 10 raised to the power negative 3. Now this one is raised to that power, which is 1. Therefore, what do we get? I've got our rate constant is given by 3.147, and in this case the overall rate order is 2 plus 1, which is equal to 3. Therefore, you have to be very careful with the rate constant. Let's say, for example, since the rate constant is given by the rate which is in moles per second divided by the rate order we've said is raised to power 3. Therefore, our overall rate constant formula would be in moles for negative 2, then per second. Therefore, this answer will be raised to negative 2 per second. Oh, sorry, it's 3.147 times 10 raised to power 10. 3 times 10 raised to power 10 per second per mole squared per second. So that will be our rate constant K. Now we go to our third method, which we call the log method.